correct me if they're wrong, I go on other ones, is from this textbook, and I use these two chapters, but I stray significantly from them, and the questions will be in the chapters as well as in the class. If you care about exams, which most of you, I think, this is your peers. Okay, so what are we going to talk about? Well, today we're going to cover most of it, and on Friday we'll get to the really interesting part, which is how the kidney gets rid of acid. So first off, we're going to talk about what we're talking about. Lay the groundwork for what I mean when I say acid-base, acidosis, alkalosis, metabolic acidosis, respiratory acidosis. So we know what we're talking about, as well as we can say right now. Then I'm going to talk about the most essential, but something often overlooked, but is fundamental to understanding the different clinical states of abnormalities in acid-base, and that's buffers, and what they are and how they function within, well, us, people, in my case, children. Then we're going to spend a while talking about how the respiratory system functions within acid-base status. Both the kidneys and the lungs can cause, so primary pathology will cause alterations in acid-base, but the complicating factor is that they will respond to the other organs. So the kidneys are sick, can't excrete acid load, the lungs will compensate. So they can either be primarily at fault for disorders of acid base, or they could be responding to a disorder in acid base. And we'll talk about both. Friday we get to talk about my favorite aspect, which is how the kidney gets rid of it. And I'll throw in a little bit of pathology. And I think it's easier to remember things when you see a kid or an adult who's sitting in front of you that's sick. If you can think about the physiology and the pathophysiology, why they're sick, it makes it more relevant, in my opinion. Perhaps not for you, but that's what you get. So, why do you need to know about acid-base status? Why do you care? Well, the problem is that anytime your cells do work, anytime you do work, your muscles contract, your heart beats, your stomach moves food through it. We do cellular work, and that has the inevitable consequence of generating acid. And if we don't get rid of the acid, what happens is this. You die. And it's not just because it prevents you from dying if you don't get rid of acid. It's because buffering your acid maintains your pH within all the cells in your body, within your brain, within your heart, within your lungs, enables the proteins there to most efficiently perform their function. On the right here, I have a nice paper from JDC in 56, which shows that there are optimal pHs at which different enzymes do their task, or the reason for existence. And I showed three here. At the bottom is trypsin. You can see at lower pHs, it's less inhibited. Same is the case for chymotrypsin, but there is a specific region which all enzymes, these are the two digestive enzymes which are exposed to different pHs in the gut. But if you look at cholinesterase up here, which is a neurotransmitter, even neurotransmitters need optimal pH for which to work. So we need to maintain different aspects of the body with specific pH. So it's not just so you don't die so that you can work most efficiently and function most effectively. That's what we need to maintain pH. Going the right way. Okay. So just out of curiosity, this is what happens, and it's kind of scary, and having seen it happen in several cases. So if you become acidic and you cannot get rid of your acid, you're kidney failure, or you're unable to breathe effectively, so you cannot excrete acid as water and CO2 from your lungs. First thing that happens is your heart beats less effectively, so slower. You get these prolonged sort of widening peaks. Next thing that happens is you should try to compensate by blowing off CO2, so you will breathe faster. You're hyperventilating. Then what happens is that the protons will be buffered into the cell, and the cell will therefore release potassium into your circulation, which causes elevated hyperkalemia, potassium, chaos, and that is really bad for your heart. You get cardiac reduction abnormalities, and then you start, instead of working normally without a normal QRST, you get what effectively are these signaling processes, and eventually the heart just gives up and it stops beating altogether. So that's what happens over the course of minutes to hours when your pH drops below a normal physiologic range. We're talking below 1.107, depending on how old you are and how well your heart is, and other factors. Okay, so enough drama, let's get back to physiology. So, the definitions, what are we talking about? So back to, I don't know, you guys do this now, you guys didn't go grade 8 or grade 9. You guys probably do grade 5, so you should go out and learn it. But an acid, which we're talking about the same thing, is a molecule or ion that can function as a proton donor. So we've got this HA gives up a proton. Protons, we're talking about pH measures protons, not by time it's protons. Basically the opposite, it mops up. It will bind a proton that's in solution and form this guy. It can be a molecule or an ion, all right? So, let's go to grade 11, perhaps. pH is the negative log of the hydrogen ion concentration. Why do we use negative log of hydrogen ion concentration? Because saying pH 7.4 is much easier than saying 30 nanomolars of protons in the log. It changes the paradigm slightly because it's a negative log, so it's inverses the scale. So what's normal? So in the arterial blood, it's 7.35 to 7.45. They say 7.4, but we give you plus or minus 0.05 pH units. It's small, just like 10 nanomolar changes that the body's offering. And this is fundamental. The cells, where the work's going on, where the acid's being produced, not surprisingly, are slightly more acidic. So remember, it's the inverse scale, so there's more protons in the cells, so the pH is slightly lower. Usually about 7.2, but they say depending on the cell how much work being done, 7 not to 7.2. Okay, so then we're going to talk about how we keep pH constant. How do we prevent it from going up or down? And one major thing that we do in high school chemistry is buffers. And there's a lot of physiological buffers. And these are essentially our weak acid and its salts, or typically a weak acid in the body, but it can be a weak base in its salt, which resist change to pH. What does that mean? It means essentially what we're seeing here. A buffer is something that which, when we add either strong base or strong acid, we have very little change in pH. So I can run a marathon, produce tons of protons that get dumped in my circulation, and then they get mopped up, and I don't drop my arterial or pH much below 7.4 because they're buffering. We have other compensatory mechanisms we'll talk about as well, but that's the first one. So we produce a lot of acid, and we're going to change in pH because it's being mopped up by a buffer, and that's what's achieved by the buffer. All right, so that's the pathophysiology. Patho being abnormal, essentially. You're going to notice I talk more about the abnormal because that's what I deal with. No one calls me to say, oh, normal pH, they call me to say the pH is abnormal. So I'm more familiar with that, but I think they're normal as well. So acidosis. And one is acidotic with a pH less than 7.35. Full stop. Alkalosis. Your blood is alkaline. So the pH is greater than 7.45. These are strictly clinical definitions. We take your blood, we put a microelectrode and we measure the concentration of proton, transfer that into a pH. If it's less than 7.35, you're acidotic. Greater than 7.45, you're alkaline. Okay, not really useful. What is more useful is trying to determine the type of acidosis or alkalosis, which talks to the etiology or the reason why your pH is normal, or your patient's pH, or your dog's pH. So there's essentially two general mechanisms. One is a respiratory, the other is metabolic. Respiratory is the acidosis, or alkalosis, is due to alterations in respiration. Therefore, you have a primary change in CO2. So if your blood pH is less than 7.35 and your CO2 is elevated because you're not blowing it off with higher, it's respiratory acidosis. Respiratory alkalosis is the opposite. You have an increased pH and your CO2 is low because you're breathing really quickly. This is classically what you see in blood work on 5-year-old kids who come in to have someone walks in front of them with a needle saying, I need to take your blood, and they go, you can all blow your CO2 off and increase your pH in your blood, just by getting stressed and having anxiety. So that's what a respiratory alkalosis is. It's not terribly pathologic. There are other reasons you breathe too quickly. You go out, you take methamphetamines, that will make you breathe, but really cause respiratory alkalosis. The other general category of alterations in acid-base are due to either your kidneys or another metabolic factor. It's typically not your kidneys, that's less common. It's usually because we dumped in an acid or a base. What do I mean by that? Someone's gone out and they've taken an acid base. The silic acid can be classic as aspirin. They got mad. Say their girlfriend dumped them and go out and take a bottle of aspirin. That's the diet. You take exogenous acid. Typically, and that's where the metabolic acidosis is typically from. Metabolic alkalosis is the opposite. You ingest baking soda for some reason. You're a 6-year-old kid. It was good for whatever reason. They think it tastes good, so they eat too much of it, and therefore you get an elevation in alkaline. You can also have primary renal dysfunction, which causes this as well. And I believe you guys have to write an essay, right? I think I put an essay for you. One of my essays talks about the primary diseases of the kidney, single channel disease that causes. Sorry. I could talk higher. I'll just talk on the stairs and just tell me well if it's an issue. I realize I'm not exactly the best at articulating. Is that better? Okay. So, simply put, respiratory abnormalities are changes in ventilation, causing changes in pH, metabolic, or due to too much exogenous acid and base, or primary kidney problems, which is what I should take to do. Okay, so now we're going to talk about what your body does to deal with these problems. So today we're going to talk about buffers, first line of defense, really fast. We're then going to talk about how your respiratory system can alter its ventilator status to compensate for changes, and or how when it's broken it causes changes. And then on Friday we'll talk about what my passion is, which is how the kidney controls proton and other ion movement across different nephron segments. Okay, so buffers. Bicarbonate being the most common. It's by far and away the most common extracellular buffer. It's at 20 to 30 millimolar concentration. That's quite large in the blood, in potassium in the blood, more than really any other ion other than chloride and sodium. Phosphate and proteins, generally intracellular buffers, but your cells in the intracellular bond make up a large chunk of your volume, so this is an important buffering system when we talk about the whole organism. Proteins are also often floating around in your blood as albumin or as other large molecules, and they can act as buffers within your blood as well. So typically people think about them as intracellular buffers, although they can be a significant extracellular buffer. Right, buffers, let's go back to this. This is key. First line of defense. Generally, a weak acid takes up protons so as to minimize alteration of free acid. This is typically we think about buffers working when they're acidotic. They do have an effect on more alkalotic, but acidosis tends to be even more significant pathological condition. Happens quickly, really quickly. We're talking microseconds. All right. I don't know how much biochemistry you guys have to do, but this guy, Henry Hasselbach, described the relationship between a buffer and its conjugate base. And the equation he provides is this. pH is equal to the pKa. So that's, the pKa is the point of inflection of this titration curve. You can titrate with an acid or a base. With an acid, obviously, it goes this way. Plus the log of the acid over its protonated form. Importantly, as we probably learned in high school, but it's the same. I mean, all these things we build on as we go through our studies, it applies to different systems. So just because you do it in a test tube, it also applies in your red blood cell, it applies in your plasma. So you can titrate plasma. When people do these experiments, people titrate the plasma of animals. We tend not to do it with people. Sometimes we have to clinically get them back in normal range. But you can apply. You can imagine if you have a canine who is acidotic, you can add to his circulating volume of bicarbonate. You can perform essentially this titration curve to see at which point you have a point of inflection and get your pKa. So it applies Importantly, we should remember that the resistance to changing pH is both specific to the buffer, but also to how much buffer you have. So the concentration of buffer within the plasma. And that's why bicarbonate tends to be a good buffer because it's at a higher concentration or within the cell. All right, so you're going to see this equation a lot. I like this equation. It's an important equation. It's fundamental to all of our systems, sitting, writing, thinking, walking through classes. What does it tell us? Many, many things. But let's just go through the equation first. What happens? You've got very simple molecules. Water, carbon dioxide. They will, in the absence of this enzyme, carbohydrates, form carbonic acid, which rapidly dissociates into bicarbonate and a proton. However, in the presence of carbonic acid, this occurs very, very quickly. And by sequestering carbonic acid in specific locales within the body, specifically cells within different nephron segments and within the red blood cell, enables us to control this equilibrium and use this gas as an effective buffer. And I will reiterate this. Okay, again, equation, bicarbonate and proton becomes carbonic acid, doesn't exist very long. It generally gets shuttled via carbonic anhydrase into water and CO2. As this is a buffering system, we can describe this situation using the equation derived by Henderson and Hasselbalch. And it looks like this. pH is equal to 6.19 plus log of bicarbonate over CO2. We can measure CO2 and bicarbonate in the blood and infer pH, or work the other way around. This is very useful clinically. So what's important about this is it shows that CO2 is in fact an acid. It's a weak acid in your body. You think about CO2 as a gas. It is an acidic gas. If you bubble it into a solution, that solution will acidify. If it is in your periphery, when you perform metabolic work, when you consume glucose and produce carbon dioxide, it acts as an acid in your periphery. So this is an acid. Now, I told you that the buffer works best when known as pKa, and I'm telling you now the pKa of this buffer is 6.9, or 6.1, which is roughly 1.3 pH units, which is a lot. This is a log scale away from what we want physiologic pH to be. So intuitively, one would think that this is a terrible buffer. However, because of minute ventilation, we can control the concentration of CO2 so acutely and quickly. It is a highly effective buffer. You can breathe quicker or slower. You don't even think about this. It just happens. So it becomes a very useful buffer because CO2 is a gas and you can exchange it so rapidly. Okay, talk a bit about phosphate. So it's tricoated at an extremely low pH. You can gain or lose protons. But what's important is that in the dichroic state, between the dichroic and the monochroic state, the pKa is 7.2. So within the intracellular milieu, it's at the perfect pH, so there's changes. So it's a very good intracellular level. Now, proteins are an interesting situation. So proteins, amino acid chain containing histidine. Histidines have this monodental ring, which is easily protonated. The pKa of the single amino acid in solution is 6. Depending what you do to the surrounding area, this pKa can be greatly increased or decreased. So typically within a cell, what's happening is you're protonating and deprotonating histidine residues on polypeptide chains / proteins. We'll talk about a really specific example. I think it's interesting, your textbooks never think about this or talk about it, and it's useful to think about because of the height of respect to vitamin D and bone disease. Your bones are made up of calcium carbonate. Carbonate is a buffer for cells, and calcium phosphate. So they're a brilliant buffering system, and they can release protons or consume protons in the blood. And essentially what simply one needs to remember is that your skeleton will get dissolved by acid. And so if you leave children or adults at acidic pH for a long period of time and allow them to hypoventilate, they will dissolve their skeleton and have lost their pH. So there are other effects than on your heart. Your bones will get unwell if you don't deal with your acid-base status. All right, so we summarize and leave buffers where they are. First line of defense, very important, often removed. Respond to changes in pH exceedingly rapidly in the microsecond range. Important buffers include bicarbonate, phosphate, and proteins, especially hemoglobin. And don't forget about the bones. Bones are also playing a role here. All right, now let's talk about the lungs. So I realized when I was going through this last night, this slide sort of doesn't make a heck of a lot of sense. But essentially, this is what we're going to talk about in the next 20 minutes, 25 minutes. So we just suggested that carbon dioxide is an acid, and I need to reiterate that because its movement allows us to move acid from the periphery to out of your body. And then we'll talk specifically about how that occurs, and we'll get into some of the molecular details, although we're not supposed to do too many, otherwise big molecules, so I try to keep it to a minimum. Then we'll talk about the movement of protons and the movement of the gas itself, CO2. Because it follows a similar pathway, and it's useful to draw that parallel over here. And then finally, we're going to talk about the response of your respiratory system to the application of exogenous acid, be it as carbon dioxide or as a figurative acid, HCl. Again, CO2, bubble it into your cells, bubble it into beaker, into acid, because it interacts with H2O. In the absence of carbonic anhydrase, to form carbonic acid, bicarbonate in a proton, carbonic anhydrases in red blood cells, and specific Nephron systems, which we'll discuss prior. Okay, so here's the problem. Here's the largest problem. Just sitting here, not running, not doing anything, just sitting here listening to me, we're all making 230 mils of carbon dioxide per minute. We're not making that, we're making a very small amount of that in the alveoli where it can diffuse out. Most of it we're making out of large muscle groups. Now, the next problem is that only 23 mils of this is dissolvable in the plasma or blood, the plasma component of blood. So that means 90%, or roughly 207 mils, have to find another way other than by being dissolved directly in the plasma to get from your muscles to your alveoli and into the atmosphere. So the first solution, which accounts for 30%, is that CO2 will bind to hemoglobin in the periphery in your red blood cell, forming carbaminohemoglobin, which can be transported to the lungs. So not only does oxygen, it does hemoglobin bind oxygen in the alveoli in your lungs, take to the periphery, it binds CO2 in the periphery, it takes to the lungs. So that's the first response. You may or may not know that. I don't know if you teach that in high school now, probably. So here's the reaction again, CO2 binding to load. Does anybody know how to make this go back on when it wants to turn itself off?
Start the video.
It's
Did you
just
see
decided
that?
to stop.
Maybe you have to just change the output.
Anybody have a solution?
I don't know.
All right, let's do it on the board. Or not. All right, so we've got roughly half the talk about. And we can.
Did you change the output? I don't know how to do it though. Just like, you know how it said to change the video at the top? I thought maybe he actually changed the output or whatever, because you know you can change it to like. But he has like a clicker, doesn't he? To switch the slides? I don't know, I wasn't paying attention.
That's cute. Oh, that's so cool.
Okay, I'm just gonna stop.